This lecture is on Sun Tzu's Remainder Theorem. So this is one of those theorems in number theory that is based on a relatively simple idea, but the more time you spend with it, really, you start to realize that it's actually saying something extremely deep. So it's similar to Euclid's algorithm in that respect. And the idea behind this theorem is that we would like to combine information about divisibility by multiple numbers at a time. So modular arithmetic, which is what we've been studying for the past couple of lectures, that gives you information about divisibility by one number at a time. So we're sort of zooming in on the integers, just looking at divisibility by one number at a time. Let's say we look at a different number. Well, we get some different information. And the question is, can we sort of combine that information into sort of one single piece of information? Can we sort of zoom out a little bit? And so here's an example kind of problem you can solve with Sun Tzu's theorem. So suppose I have some number of objects. So suppose I have, let's just say n objects. And then when grouped by 3, so I'm putting groups of 3, there's one left over. Okay. And then when grouped by, let's say, 5, there's 2 left over. How many objects are there? Okay, so what is this saying? Well, we have a new language to describe this kind of thing. That's modular arithmetic. So when grouped by 3, there's 1 left over. That means that our number n is congruent to 1 mod 3. So to form 3n plus 1, or 3k plus 1. So n is congruent to 1 mod 3. But it's also congruent to 2 mod 5. It's 2 more than a multiple of 5. Okay. How would we solve this problem? Well, one approach is to take this information one at a time. So let's look at this one first. So if n is congruent to 1 mod 3, well, that means n is of the form 3k plus 1. So n could be, well, it could be 1, it could be 4, it could be 7. See, I'm just adding multiples of 3, etc. And then what we could do is we could just check each of these one at a time to see which one is congruent to 2 mod 5. So let's go ahead and do that. So is 1 congruent to 2 mod 5? No, that's 1 mod 5. 4 is 4 mod 5. 7 is indeed 2 mod 5. So 7 is the number that we're looking for. So check 7 is 1 mod 3. Yes, and it's 2 mod 5. So there are 7 objects. Well, technically this is a little bit incorrect because I could now add the GCD, not the GCD, the LCM of 3 and 5, which is 15. So if I do 7 plus 15, I get 22. And 22 differs from 7 by a multiple of 3 and a multiple of 5, right? A multiple of 15. So it will also satisfy this congruence. So I could have also had 22 objects. I could have also had, I could continue adding 15s, right? So I could have 37 objects, etc. So really, when I say 7 objects, I mean 7 mod 15. Okay. But we've sort of narrowed down what n can be. So here we know if n is congruent to 1 mod 3 and simultaneously 2 mod 5, then n must be congruent to 7 mod 15. Okay, so what else can happen here? So suppose we have a slightly different system of congruences here. So another example. Say we have the same kind of problem, but let's say n is congruent to 1. Let's change the modulus a little bit. So mod 4. And n is congruent to 2 mod 6. So now what is the solution? Well, turns out this one does not have a solution. Why is that? Well, so this is not possible. Why is that? Well, if we think about this first one, if we're 1 mod 4, we're to form 4k plus 1, we're definitely going to be an odd number. All right, so something of the form 1 mod 4 is an odd number. So this is sort of saying it's odd. So n is odd. But in this one here, if we're to form 6 and 6k plus 2, we're going to be an even number. So this one is sort of saying that n is even. And that's a contradiction. We can't have both of these. There's some sort of incompatibility. Mod 2. So one of these is saying I'm odd, one of them is saying I'm even. So this type of problem is not always possible. And to understand exactly when this type of thing is going to be possible to solve, there's a really nice visual approach to this. So what I'm going to do is draw a grid here. So I'll do a 3x5 grid first. And then, so 3x5, I'm looking at these moduli here. And then over here, I'll draw a 4x6 grid. I'll tell you what I'll do with these grids. Okay. So in this one, I'm going to start with the numbers. So this side will be mod 3, and this side here will be mod 5. So I have 0, 1, 2, and if I mod 5, I can be either 0, 1, 2, 3, or 4. And here we'll do mod 6 going across the top and mod 4 over here. So 0, 1, 2, 3, mod 4, or I can be 0, 1, 2, 3, 4, or 5 mod 6. Okay, what am I doing with these boxes? So I'm going to just start considering integers. Okay, for example, the integer 0 is both 0 mod 5 and 0 mod 3. So 0 will belong to this box here. Okay. The integer 1 is 1 mod 5, and it's 1 mod 3. So I'm going to put the 1 in this box here. Right? So I can put any integer in one of these 15 boxes, depending on what it is mod 3, what it is mod 5. 2 is 2 mod 5 and 2 mod 3. That'll go in that box. The number 3 is actually 0 mod 3, right? And 3 mod 5. So 3 will go up here. And you can see what's happened is I started going down diagonally, but then I sort of wrapped around the top here. So, and then the next number you might guess will be here. So 4 is 4 mod 5 and 1 mod 3. The integer 5, I would guess that it will continue this pattern, and so we'll end up wrapping around this side. And indeed, 5 is 2 mod 3 and 0 mod 5. And you continue in this manner. So I can keep filling in integers. 6 is 1 mod 5, 0 mod 3. And then 7, 8, 9 is going to wrap around 10, 11, 12, 13, 14. Very nice. And then the 15 would have gone in this top left corner if we continue this pattern, which is where the 0 is, which is 0 and 15 are congruent, mod 15. Okay, so we were actually able to fill in every box with exactly one number from 0 to 14. Okay. And we can see actually our solution here. So 7 mod 15, 7 is right here. And that is sort of the unique number, mod 15, that's congruent to 2 mod 5 and 1 mod 3. Let's do it with this one. So 0 is 0 mod 4 and 0 mod 6. 1 is 1 mod 4, 1 mod 6. 2, 3, 4 is going to be up here. 5, I'm just filling in the integers. And then 6 would have been in this box, so that corresponds to this box over here. 6 is 2 mod 4 and 0 mod 6. And I get 7, 8, 9. Do you see what's about to happen here? So 10, 11. Now, where is 12 going to go? Well, the pattern is sort of leading me back to here. And indeed, 12 should go in this box. But it's already occupied by the 0, because 12 is 0 mod 6 and 0 mod 4. So it's sort of 0 or 12. So I'll put a little 12 here. And then 13 would have gone in this box, 14, 15, etc. So every box actually gets filled in twice with the integers from, let's say, well, there are 24 spaces here. So if I go from 0 to 23, I will fill in every box twice, and there will be some boxes that are missed completely. And we actually see one of those. If my n is congruent to 1 mod 4 and 2 mod 6, that's this box here. But there's nothing there, right? We already reasoned that there can't be anything in this that satisfies both of these simultaneously. Okay, well, what's going on here? So let's take this box over here, so mod 3 and mod 5, and I want you to actually notice that we can solve not only our original problem, we can solve any problem of the form x is congruent to a mod 3 and x is congruent to b mod 5. And what do we get? And we get a unique solution. Not in the integers, right? Because I would have put the 15 there and then the 16 there. But we get a unique solution. Mod 15. Modulo 15. Okay. We're able to put in all the numbers from 0 to 14, and they each occupy their own box. Let's try to actually prove this. And you might have the feeling that it has to do with sort of the primeness or the relative primeness, at least, so the 3 and the 5, these dimensions here. And that's indeed the main idea of the proof. So let's try to prove it. So suppose, what do we want to show? We want to show that every number gets its own box from 0 to 14. So suppose there are two numbers among these, just all the integers from 0 to 14, so 0, 1, 2, to 14, in the same box. Okay, what would that mean? That would mean that, let's call these two numbers something. So we'll call them A and B. So that would mean that A is, actually I already use, oh, okay, that's fine. So A and B, so that means that A is congruent to B mod 3, certainly, and A is congruent to B mod 5. That's what it means to be in the same box here, right? They have the same congruence conditions, mod 3 and mod 5. Okay, so then we have this. And what would we like to do? We'd like to show that actually A and B are the same number. At least the same number mod 15. How do we do that? Well, let's translate this over to a statement in integers. So that's what we've done many times before. This is saying A minus B is multiple of 3. And A minus B is also a multiple of 5, but it's a different number here possibly. So 3K and 5L. Okay, where do we go next with this? So the idea is we want to show that actually these differ by a multiple of 15. So somehow, if we look at this first equation, this k we want to show is actually divisible by 5. And we can actually do that. The reason we can do that is, well, 5L equals a minus b, which equals 3k. So 5L equals 3k. So in particular, 5 is going to divide 3k. Right? By definition of divide. But 5 does not divide 3. We want to conclude that 5 does divide k, and we can conclude that by Euclid's lemma. And that's because 5 is prime. So 5 is prime. So by Euclid's lemma, we're using Euclid's lemma here. Remember what Euclid's lemma says is that if a prime divides a product, then that prime must completely divide one or the other in terms of the product. It can't sort of be split into both of them. So 5 is going to divide 3, or this is what Euclid's lemma says. 5 divides k. And of course this one is nonsense. So 5 doesn't divide 3. I can say the symbol does not divide 3. So we conclude that 5 divides k. Well, that just means that k is some multiple of 5. So k is 5c. And now if I take this first equation, I can write a minus b is 3 times 5c, which is 15c. So a minus b is a multiple of 15. What does that mean? It means a and b are congruent mod 15. So a is congruent to b mod 15. Okay? So among these 15 numbers here, these represent all the congruence classes mod 15. So a and b actually just have to be the same number here. So we essentially proved there cannot be two different numbers among these in the same box here. But what did we use? We use this very powerful statement, Euclid's lemma. Euclid's lemma says if a prime divides a product, it has to divide one or the other factor in the product. That's exactly the part of the argument that breaks down when we have this box. Okay? If we got to this point, we would conclude 6 divides 4k. Does that imply that 6 divides 4 or 6 divides k? Actually, it doesn't. Let's say k was equal to 3. 6 certainly divides 12, but 6 does not divide 4, and 6 does not divide 3. So this is not true. Not true because 6 is not a prime. Okay. We can actually generalize Euclid's lemma a little bit, so we'll do that a little bit later. So just to recap what we've done, we've shown there's exactly one number here in each of these boxes here. So we've shown each box has a unique number among 0, 1, 2, up to 14. What have we not technically shown? We have not technically shown that there has to be a number in every box. Okay? We just showed that if there's a box with a number, it can have at most one number, in other words. So we've shown every box has so technically we haven't shown this. So we've shown if it does have a number, it has a unique number. So it has at most, I should say, at most one of these numbers. Okay. Well, it turns out that actually proves that there has to be a number in every box. And the reason is there are exactly 15 numbers here. Okay. if I put those numbers in these 15 boxes so that every box has at most one number, the only way I can do that is to put one number in each box, okay? Because it's the same cardinality of these sets. So this implies every box has exactly one number. Since there are 15 numbers here, and there are 15 boxes. 15 boxes. Okay. So let's now state the first version of Sun Tzu's theorem. So yeah, let's do it down here. So Sun Tzu's theorem. Sun Tzu's remainder theorem. The word remainder comes from just having things left over, thinking about these congruent statements as remainders. So when I divide my objects by 3, there's 1 left over, so I can treat 1 as the remainder. Okay, so how is this going to look? So if I have a statement of this form, so if x is some number that's congruent to, say, a mod m1, let's say a1 mod m1, and x is congruent to a2 mod m2, well, what's the conclusion? Well, there is no conclusion unless we also impose the following. So if we have this, it's like a system of congruence equations, and we know that the moduli are coprime. So, and the GCD of the moduli are coprime, is 1. That's what it means to be coprime. Then there exists a unique solution to this system of congruences. So there exists a unique solution modulo. It's not a unique integer, but there's a unique solution modulo the product of these two, just like we took the product 3 times 5. So modulo m1, m2. So that's Sun Tzu's remainder theorem, or Sun Tzu's theorem. And there are really 2 parts to this statement: existence and uniqueness. And I'm going to try to prove this theorem, and our strategy is going to be to basically just imitate what we've done here. Except, as I hinted at, we're going to need a slightly more general version of this Euclid's lemma, as we're not assuming that these moduli are actually prime. We're just assuming that they don't share any prime factors. Okay. Here it turned out our moduli were both prime. We can do this more generally. So there are 2 parts. So first of all, let's do... what do we do here? We sort of did the uniqueness part first, and then used the fact that the cardinality of these 2 sets were equal to prove that there exists actually something in every box. So let's just try to duplicate this. You can imagine there's a big box of dimensions m1 and m2 if you'd like. But we're trying to show that you can put in all numbers from 0 to 1 minus this one into the boxes so that we don't ever duplicate and so that we actually fill every box. So let's look at the uniqueness part first. Suppose we had 2 different solutions. Okay, so suppose we had 2 different solutions modulo m1, m2. So suppose x and y are solutions to this system such that, so with x just being congruent to y, yeah, so again, we're going to say they're actually in the same box. Okay, so x is congruent to y both mod m1, and x is congruent to y modulo m2. We'd actually like to show that these conditions imply that x and y have to actually be just the same modulo m1 and m2. So they have to be congruent modulo m1 and m2 as well. So if we had 2 different solutions to this, they have to be congruent modulo m1, m2. And the way we're going to do that is just the same that we already did. So first of all, what does this mean? This means that x minus y is a multiple of m1, called m1k1. And at the same time, that x minus y is a multiple of m2k2. And what we would like to do now is show that actually x minus y has to be a multiple of the product. And remember, our approach was to try to get m2 into this first equation somehow. You can also try doing things like multiplying these two equations, but it turns out that it doesn't really get us what we need. So we really need to use something deeper here, which is some version of Euclid's lemma. So here's what we want to do. We know that these two things, they both equal x minus y. These are as integers even, right? So m2k2 is the same integer as m1k1, which in particular implies m2 is going to at least divide this product. Okay. And the problem is m2 is not prime. So we cannot use Euclid's lemma. However, we can use a more general version of Euclid's lemma. This will actually give us an opportunity to recall the proof of Euclid's lemma, which is always good to do. It's such an important statement that it's good to understand this one fairly deeply. So the more general version of Euclid's lemma is let me go to this one. So if I have any number dividing a product, so some divisor of a product, and we don't need D to be prime, we just need the GCD of D and one of these things in the product, let's say A, is 1. So if D is coprime with one of the factors in the product, well, I can maybe guess what that'll imply. That implies that actually D has to divide the other one. So D has to divide B. Okay. Why is this true? Well, how did the proof of Euclid's lemma work? What we did was we took this statement and we used the Euclidean algorithm to write 1 as a linear combination of D and A, dx plus ay. And then there was a really neat idea to multiply this by b, because we want to get b and introduce b into this equation somehow. This gives us b equals b dx plus a by. And what do we conclude? Well, d clearly divides this term. D also divides this term. Do you see why d divides that term? Well, we're assuming it, right? So nothing deep there. D divides AB. D has to divide their sum, which is B. So that implies D divides B. It's essentially exactly the proof of the usual Euclid's lemma. It's just we realize we don't actually need this to be prime. We just need it to have GCD 1 with one of the two factors. Okay, so returning to our situation, this means that we can say that M2 either divides M1 or M2 divides K1, but M2 cannot divide M1 because they're coprime. I mean, I should also say that whenever I'm working with moduluses here, the modulus is not equal to 1, let's say. So the only number, modulo 1 is 0, so these are both greater than 1. But we conclude that M2 has to divide K1. So what do we do before? We wrote this K1 now as M2 times something. So x minus y is M1, M2 times something. But this clearly shows that x and y differ by a multiple of M1, M2. So x is congruent to y mod M1, M2. And that proves the uniqueness part of Sun Tzu's theorem. Okay, so there exists a unique solution is what we want to prove. We proved that if there is a solution, so if we did have two solutions, they actually had to be the same solution. How do we prove there exists a solution in the first place? Well, it's just like how we did before. So existence there are m1, m2 possibilities. We have a congruence modulo m1, m2, so there are m1, m2 possibilities for x. But there are also m1, m2 possibilities for, so m1, m2 possibilities for x modulo m1, m2. But there are also m1, m2 possibilities for my choice of a1 modulo m1 and a2 modulo m2. Okay, so these are like the numbers 0 through m1, m2 minus 1, and these are like the boxes. Okay. But what we just proved? We proved that each one of these kinds of congruence systems of congruence equations has a unique solution if there is a solution. So there's at most one number per box. Okay, but they're the same number of numbers in boxes. So these sets have the same cardinality, and we already proved uniqueness. So these have to be there has to exist a solution. Okay, so that is Sun Tzu's remainder theorem. But what I'd like to do now is actually show you Sun Tzu's original problem. So Sun Tzu was a this is not the Sun Tzu who wrote Art of War, by the way. This is a mathematician, Sun Tzu, who lived I think several hundred years later. This was his original problem. This was in third century China. Problems like this were considered. Okay, here's the original problem. It was the same kind of thing with objects. So suppose I have X number of objects, and if I group them in threes, so modulo 3, if I group them in threes, there are 2 left over. So x is congruent to 2 modulo 3, x is congruent to 3 modulo 5, and x is congruent to 2 modulo 7. So if I group them in by 7s, there's 2 left over. And Sun Tzu's problem was, how many objects are there? So what is x? Okay, how do we do this? Well, this seems to add another layer of complexity because we now have 3 equations. So we could try to do a more general version of what we did before. So we had a sort of a two-dimensional picture. We could instead look at something like this, I suppose. We have a 3-dimensional kind of a solid block here, where we're sort of filling in all the numbers, going down the diagonals, this 3-dimensional block. There's another approach, though. We can keep this a 2-dimensional problem by first choosing 2 of these. So let's first choose these 2. I'm going to ignore the third one for now. So pretend this doesn't exist. So we're just going to solve this first one. So these will give me a solution modulo 15 by this first version of Sun Tzu's theorem. I should say there are actually many versions of Sun Tzu's theorem. This is a theorem that has been vastly generalized. But which is one sign that it's a really important theorem. Okay, so x is congruent to something mod 15. What is that something? Let's see if we can just come back here and stare at our chart. So x is 2 mod 3 and 3 mod 5. If we're 2 mod 3 and 3 mod 5, then we have to be 8 mod 15. So it's congruent to 8 mod 15. Here's what I'm going to do now. I'm just going to replace the first two with this new one. So x is congruent to 8 mod 15. Notice 3 and 5 are coprime. I also want you to notice that 15 and 7 are now coprime. We definitely need everything here to be coprime. In fact, we need the moduli to be pairwise coprime. I'll get into that when we state the general theorem. But essentially, we've turned our original 3 equations into 2 equations. And now we can try to solve this. You know, just to be honest, so there's another method I'm going to show you in just a second. But if I had this problem and I needed to solve it, I would just start counting by multiples of 15. So I'd start with the 8, try 8 plus 15 is 23, 23 plus 15, 38. So I'm just going up by 15s. I know I have to be congruent by, I know I have to be congruent to 8 mod 15. What's next after this? Well, actually, let's check to see if we found it already. So if x is congruent to, that's not congruent to 2 mod 7, that's 1 mod 7. 23, I think we just got lucky, right? 23 is congruent to 2 mod 7. So this is congruent to 2 mod 7. And it's congruent to 8 mod 15. But if it's congruent to 8 mod 15, it's congruent to 2 mod 3. That does work. And 3 mod 5. That also works. So 23 is our solution. And it turns out 23 is a unique solution. It's a unique solution modulo 15 times 7, modulo 105. So if we have more than 2 equations, we get a unique solution modulo the product of all these, as long as that product, as long as these numbers are coprime with each other. So you might be wondering, was this seems a little bit haphazard, just to count by multiples. Is there a better way to maybe get this solution? For example, is there just a formula maybe for this solution? Give it, like, feed in these the system of congruences, and somehow tell me that it's 23. So is there a formula for the solution? And it turns out the answer is yes. It's actually just a really nice idea. I've always found this to be really ingenious. And the idea is we're just going to simply write down something that's so it's not going to be simple actually, but we're going to try to construct a solution. I'm going to have 3 parts. This is going to be this part here. This part here. I'm going to write down an integer, which is going to work for this. And this part here. So yeah, I'm writing down something in Z. Here's how I'm going to construct it. I'm going to keep in mind that, so I'm going to think of this part as sort of my mod 3 solution. And this part as my solution. And this part is my mod 5 solution. And this part is my mod 7 solution. Okay, well this seems hopeless because, fine, if we find a mod 3 solution, how do we know these aren't going to mess it up, right, when we add more things to it? And the way I'm going to ensure that is I'm going to construct these 3 numbers so that when we go modulo 3, this one's going to end up being my mod 3 solution, 2, and these 2 are just going to end up being 0. When I look at x modulo 5, these 2 are going to end up being 0, and this is just going to be 3 modulo 5. And then when I look modulo 7, these 2 are going to end up being 0, and this is going to be 2 modulo 7. So I satisfy these. Well, how can I do this? Well, one way to get these to one way to ignore these modulo 3 is just to put a factor of 3 in there somewhere. So I'll put a factor of 3 in these two. I won't put it there, so I do not want this to cancel out modulo 3. But these are now going to be 0 mod 3 if I put a factor of 3 in there. Similarly, I'll put the factor of 5 in these two. Okay, not the mod 5 solution, but in the other two. And I'll put the factor of 7 in these two. So that's the first thing I'm going to do. Next thing I want to do is just sort of simply write in the number that I want to get. So I want x to be 2 mod 3, right? And I want the mod 5 solution to be 3, so I want it to be 3 mod 5, and I want it to be 2 mod 7. Great. But do you see the problem now? So if I look at this mod 3, great, I get 2, and these cancel out. However, I have this 5 times 7, which is rather annoying. I would like to do one additional thing here so that the 5 and the 7 will actually cancel out when I look mod 3. And we actually do have a way to do that. What I'm going to do, let me use another color even. I'm going to throw in here, I'm a little confused even how to say this, but I essentially want to take the inverse of, the modular inverse of 5 times 7, modulo 3. So I want this, so when I write this, I want this to be a mod 3 inverse. This is a mod 3 inverse. 5 times 7, 35, that's not an invertible integer. There's no multiplicative inverse for that. But I want to take the inverse of this modulo 3. I know that this will have an inverse modulo 3 because in the previous lecture we established that a number is going to be invertible modulo 3 if it's coprime with 3. And this is certainly coprime with 3. So that's going to be a mod 3 inverse. So I need to write in this thing. And then this next one, what do I need to do? I need to do 3 times 7. I need to try to cancel that out when I look mod 5. So this is specifically going to mean the mod 5 inverse. And then I need to cancel out the 3 times 5 when I look mod 7. And see, the other terms are already going to go away because they're 0 mod 7. But I need to make sure that this extra bit here gets canceled out. So I'm going to take the mod 7 inverse. And what I just wrote down there, that should just be a formula for my solution. Let's check it first. So x is going to be, well, what is, we need to do some math here. So what is this this inverse actually going to be? So 5 times 7, let me use some scrap paper over here. So I want to do 5 times 7 is congruent to, that's 35, so that's 2 mod 3. I want to actually find the inverse of 2, meaning the solution to this, just to remind you what a modular inverse is. I want to find something to multiply it by it to get 1 modulo 3. Well, 2 works, right? So 2 is actually its own inverse. 2 inverse, just 2. Modulo 3. What does that mean? It means I can actually take anything here congruent to 2 modulo 3. So I'll just take 2 itself. So I'll write this again. This inverse here is just going to be the number 2, because 2 is its own inverse. Plus, and I've got 3 times, okay, let's look at this. 3 times 7. 3 times 7 is 21. That is congruent to 1 mod 5. When we have something congruent to 1, that's really nice. I mean, that's just going to be its own inverse as well, right? Because we want to solve 1x is congruent to 1, so yeah, 1 is going to be its own inverse. The solution to that is x equals 1. So this is going to be 1. We have times 3 times 7. And then finally here, we have 2 times 3 times 5 is 15. Let's do this in our heads, actually. So 15 mod 7, that's also congruent to 1. So the inverse of 1 mod 7 is just going to be 1. So I can just take 1 itself. I could have taken 8 or 15, just to kind of mind you what I'm doing. I'm looking at something that's an inverse mod 7. So as an integer, it can be any of these things. Let's take the simplest one. Okay, let's actually calculate this out. So what do we get? We get x is sorry, what is this? So this is 140 plus 9 times 7 is 63 plus 2 times 3 times 5 is 30. So now I'm just working in the standard integers now. And what do we end up with? We have 203 plus 30 is 233. And that looks a little bit different than our intended solution of 23. But it's not. It's the same because we know that we get a solution modulo 105. We have a unique solution modulo 105. Okay, so it looks like we had a different solution. They're actually just corresponding to the same thing. So 233 is congruent to 23 modulo 105. Okay. And this is just a really so it looks like a very complicated calculation that we did. However, this is really important for 2 reasons. The first reason is, our proof of existence before sort of relied on this, cardinality of sets argument. We had to prove uniqueness first. However, the way we're proving that a solution here exists is just by writing it down. So it's a complicated formula, but sort of by construction, this is going to satisfy these congruences. So in some sense, it's an alternative proof to Sun Tzu's theorem. I'll state the more general version of Sun Tzu's theorem down here. Before I do, the other reason this is important is this is actually very fast to do with a computer, computationally. This is very fast. And the reason is, to find these inverses, these modular inverses, if you remember in the previous lecture, what we did was we solved a equation using Euclid's algorithm. And Euclid's algorithm is one of the fastest algorithms there is. So this is one way to solve a problem like this, by just writing down a solution. And you can generalize this for different numbers here. It's the same idea. So let me just briefly state down here. So this is the version of Sun Tzu's theorem for multiple equations. And it's just the same as the other version, but we'll write it for completeness. What do I mean? It's just the same. So we can have x is congruent to a1 mod m1, a2 mod m2, ... We can have as many congruence equations as we want. So we can have divisibility by many integers here. We do have a finite list here, though. So go down to mk. And we need one more condition, so let's reason what that condition has to be. Before, we needed our moduli to be coprime. In this case, we need our moduli to also be coprime. But what do we mean by that? We mean that if you take any two, they don't share a common factor. So none of the pairs of moduli share a common factor. They're pairwise coprime, which means GCD of any two, mi and mj, is 1 for any I and j. for any I not equal to j. The conclusion is the exact same as before, and there exists a unique solution modulo. What should it be? It should be the product of all the moduluses. So m1, m2, ... take a product up to mk. Okay. So that's a more general version of Sun Tzu's theorem. Like I said before, there are even much more general versions than this. So this is a theorem that's been vastly generalized. So I'm not going to prove this because the proof is basically exactly the same as you just do the previous theorem and you apply induction. Okay. What I would like to do, though, is give you an example of how you might use this theorem to do what I was saying at the beginning, to sort of combine information about divisibility by more than one integer. So here's an example. Let's take a polynomial. Take the polynomial x squared plus 7x plus 2. Okay. And I'd like to ask a question for what values of n, for what integer is n, will the value fn, so value of this polynomial n, end in a 0. What's the translation of this? Will f of n be a multiple of 10? Okay. Well, here's when something will be a multiple of 10. It's another translation still. That means I'm congruent to 0 modulo 10. Okay. One way to do this problem is, and this is probably how I would do it, just to be completely honest, I would just try plugging in. So one idea, just try plugging in. The numbers 0, 1, 2, all the way up to 9. And see which one gives you multiples of 10. See which ones give you a multiple of 10. That's one way to do it. However, I would like to share a different way of thinking about this problem. Not so much that it gives us an easier method for doing this particular problem, but it's a very important method and just way of thinking in number theory in general. And it should give you a better understanding of exactly why certain ones of these are giving us multiples of 10. So for example, if you could try just plugging in, right? If you plug in 0, you get 2. If you plug in 1, you get 10, and then 20, and then there's f of n. Let me think. 32. You plug in 4, you get 46, etc. Some of them end in 0, some of them don't. Here's a second idea. Here's another idea. Just to use Sun Tzu's Remainder Theorem. Take our modulus of 10 and view that 10 as 2 times 5. Because 10 is 2 times 5, and 2 and 5 are coprime, it actually suffices, it completely suffices to solve this problem. Modulo 2 and modulo 5. So this is a very interesting concept. If we have a modulus that's not prime, if it has a bunch of prime factors, we can actually split it up into a product of prime factors or just and co-prime factors in general. And then the problem often will become simpler over these smaller moduli. And then we can use Sun Tzu's theorem, sort of piece it together into, at least this gives us the knowledge that we will, for every solution, if we have a solution mod 2 and a solution mod 5, we will get a unique solution mod 10. Okay, so it kind of gives us that peace of mind. Okay, so how's this going to look? Well, I'm going to solve it mod 2 first. So mod 2. One nice thing about this is our polynomial will get a lot simpler mod 2. That polynomial is x squared plus x. 2 is congruent to 0, 7 is congruent to 1. So I can just look at that polynomial. And let's say I plug in, here's my n, so 0 or 1. Then f of n is going to be 0 if I plug in 0. It's also going to be 0 if I plug in 1, because 1 plus 1 is 0 mod 2. Let's look at our polynomial mod 5 and see what when I'm going to get a multiple of 5. So I always get a multiple of 2. That's what it's saying. Always. And we can see that here. When am I going to get a multiple of 5? What values of n? What values of x I'm plugging in? Well, here are the possible values mod 5. And when I plug these in, well, let's simplify our polynomial. If we want, we can replace that 7 with a 2, right? Because we're working mod 5. So f of 0 is going to be 2. F of 1 is going to be 5, but that's 0 mod 5. F of 2 is going to be, what is it going to be? 4 plus 4 plus 2 is 0 mod 5. F of 3 is going to be 2 mod 5. F of 4, 4 squared, 26, which is 1 mod 5. Okay. So these are all the possible values of my polynomial mod 5. I want to find values so that f of n is 0 mod 10. That's equivalent by Sun Tzu's theorem, by Sun Tzu's remainder theorem, to congruent to 0 mod 2 and congruent to 0 mod 5. Okay? These two conditions are just totally equivalent. But that's not trivial. That comes from Sun Tzu's remainder theorem. Okay? It has to do with the fact that 2 and 5 are coprime. So in that situation, I can take this information and that information and piece it together. So let me just show you how I'd piece it together. Well, let's take, so these are the ones I want to look at. I want to find the values of n. So I know, let's take this one first. So there are actually 4 possibilities I can do. This one and that one. I could have that one and that one. I could have that one and that one. Or I could have that one and that one. So let's say n is congruent to 0 mod 2. And n is congruent to 1 mod 5. I could also have n congruent to 0 mod 2. And n is congruent to 2 mod 5. Okay. Or I could have n is congruent to 1 mod 2. And n is congruent to 1 mod 5. It's that pair there. Or I could have n is congruent to 1 mod 2. And n is congruent to n is congruent to 2 mod 5. That's that pair there. Right? These are the possible n's. So now the question is, will all of these conditions correspond to a unique condition mod 10? The answer is yes by Sun Tzu's theorem. And we can just sort of figure out what those are. We don't have to. Again, when the moduluses are small, you can just count by multiples. So if I'm 1 mod 5, well, 1 is not 0 mod 2, but 6 is. So 6 works there. If I'm 2 mod 5, well, 2 is already 0 mod 2, so 2 works. If I'm 1 mod 5, 1 is already 1 mod 2, so 1 works there. If I'm 2 mod 5, well, it's not 1 mod 2, so go up one more multiple of 5 to 7, and 7 is 1 mod 2. So what I have there are So there are actually 4 ways. And you can actually see how I'm constructing them. I'm piecing together, there are 2 possibilities for solutions mod 2. There are 2 possibilities for solutions mod 5. I'm kind of piecing them together in all the possible ways to get all my solutions mod 10. So it could be 1, 2, 6, or 7 mod 10. So if n is of the form 10k plus 1, 10k plus 2, 10k plus 6, or 10k plus 7, this polynomial will be the multiple of 10, the value. Okay, so that's it for this lecture. Thanks for watching.